Okay, so I was starting my introduction of Shiquan and Chad, so I want to kind of go through all of that again. But they are looking at the porting of a Geodynamo simulation code to KNLs. They're looking at the use of OpenMP as well as MPI for parallelization, and they're also going to look at tools to help understand the performance and performance bottlenecks and remedies for those things. So I think this will be of general interest to a lot of us. And with that, why don't we let Shiquan take it away?
Hello. So is the screen on?
Yep, the screen's showing and we can hear you just great.
Great.
Oh, so, I'll look for questions via chat. So if folks have questions during the talk, feel free to type them in. We'll also take breaks in between the speakers so you can ask questions at that time. So, thanks. Go ahead, Shiquan.
Thank you, Nancy. Thank you, Marcus, for hosting this webinar. So, hello, everybody. So today I'm going to talk about porting and profiling pseudo-spectral dynamo codes on Stampede2 KNL cluster. The ECSS staff on this project is Shiquan Su and Chad from NCAR and at Boulder and Nix at Knoxville. The exit allocation PIs is Professor David Gubbins at San Diego, and we mainly work with Dr. Ashley Wills at University of Sheffield, UK. So what we want to cover today is, in the part one, I will give some high-level introductions about the project, the code itself, and the KNL device on Stampede2 and our ECSS experience. And in the part two, Chad will give a lot of detailed and in-depth analysis of the code. So first is the brief introduction of the project. This project runs a homebrew pseudo-spectrum dynamo code to simulate the Earth's dynamo, exploring parameters ranges that produce behavior similar to those seen in the Paleomagnetic field modules based on the data from the last 2 million years. The main focus will be on search for solutions with generic magneto-geostrophic balance, large time variations in magnetic energies and dipole moments, and realistic complete polarity reversals. In the previous ECSS collaboration on this project, the focus is on the visualization. The ECSS staff helped the research group to generate nice visualization while visits software. As the new major computational resources, Stampede2, come online, it is very important that we have the ECSS effort to make sure that the code can fully take the advantage of the state-of-art hardware on TACC. In this new ECSS project, we migrate the code to KNL structure, find the best configurations to compile the code, perform various of performance studies, and add the setting treatment to the code. So for the pseudo-spectrum dynamo code, the Earth's magnetic field is generated by a dynamo process acting in the liquid outer iron core. Compositions of outer and inner cores are obtained from the densities deduced from seismologies. The code uses these calculations combined with thermal histories models on the Earth for the source of balance of our numerical simulation of the Geodynamo. The equations combine the effect of compositions and temperature into a co-densities and solve the Boussinesq equations of momentums, heat diffusions and magnetic inductions for the fluid velocity, magnetic field, and the codensity in a spherical cell. So the code is managed and actively developed by Dr. Ashley Wills at University of Sheffield, UK. The code is version controlled by assembler. Assembler using SVN tool provides secure cloud hostings for user repositories. It is a modern Fortune 90 code with object-oriented practice. The code is well organized under different modules, so we can identify and single out the most performance relevant part to spend our ECSS efforts. The code was running in production on Stampede previously. The PIs developed a customized fast Fourier transform to solve the load balancing problem. There was no threading treatment on the code, on the source code level before this project, but the PIs built up a parallel schema through using macros, which is a key features to allow the parallelisms floating through different levels, and it's a key for the fast and effortless threading treatment. So the numerical challenges here is a spherical harmonic formulation type of Lagrangian transform. The most computational costly part is from the Lagrangian transform. For this component, we need to calculate each radial points, and which requires a transform from a set of coefficients ALM to the value on points in the angular coordinates. So performing the sum over L for each J amounts to a vector matrix multiplications for each M, and then evaluate for each I, a fast Fourier transform is required for each J. So the most expensive part of the calculation is the matrix multiplications in the curly brackets in the first line. So the parallelization is implemented by split over the index M and N. The spheric harmonic modes present in the case L equal to M equal to 8 on the screen. In the code, the major task is rearrange the mode in the upper triangular shape into a rectangular shape, like on the right-hand side. And after that, we need to split the mode into groups of cores and the cores in each group, like the bottom part in different color. Each color represents a group, and within each group there were 3 columns. Sorry, there were 3 cores in each group. Each group represents a column. So to evaluate the transform, the data is first split into n sections in radius. Within each column group, a transpose is performed between radius point and mode, resulting in all modes for the given column group present on each core. Next, we sum over L at each theta, and this is the most computational expensive section of the code, but it is equally balanced across cores. So next, we talk about the KNL device we are working on Stampede2 and the best practice suggested by the TACC Center. There are 4,200 KNL nodes on Stampede2. Each have 68 cores, and each core can hold up to 4 threads. There are total 112 gig memory. 16 is the highest, faster, and the other 96 are the standard DDR RAM. So from the technical report, the following best known practice are recommended. We need to target our combination to AVX-512, and we need to use as many cores on the nodes as possible. And we need to look at the vectorizations, and we try to use the fast memory as much as possible. We need to manage the thread count, usually between 1 and 4. And we need to manage the MPI task count. We want to put 1 or 2 MPI tasks on each core. And then, because the 68 is a strange number, usually we will leave 2 to 4 cores free, and most common practice is we use 64 cores. So we obtain our performance report by gprof. gprof is a simple and powerful tool. We use the flag profiling. We can easily identify the first few computational intensive subroutines from the report. The executable is compiled with -G and -PG flags. And we follow the step on the TACC website. And we can see that the top 2 functions, the Fourier transform functions, use nearly up to 60% of the total time. So that's our major targets for the ECSS effort. So the profiler problem on Stampede2, when we set up the ECSS project, we plan to use the gprof and vtoom on Stampede KNL clusters, but they both require the -G, -PG flags to generate the profiling data. But the -P or -PG flag trigger a bug on the OPA drivers at that time, which will make the nodes in a non-responsive stage. We consult the TACC staff through the TACC system. We learned from John and Lars a trick to set up an alternative MPI fabrics. So the MPI will use the shared memory, but do not touch the only path driver. So the trick works for a while, but later the compiler just banned the executable with the -PG flags. So eventually we turned to use a mixed local resources for the vtoom profiler, and I just used the timing command on Stampede2 to time the jobs. So how we time the job? We time the job via 2 approaches. The first one is use the system provided time space -P functions. It prints out the real time, user time, and the system time for running an executable, and we monitor the real times. Also, the PIs already built time measuring in the code by using the function CPU_time. But the CPU_time will return the timing result with all threads. So we need to divide the number of threads in the threading cases. Another function we can use to replace the CPU time is the system clock. So next, we talk about how we use the OpenMP treatment. So here is an example. Here is the most computational expensive subroutines in the code. So we need to define the threading treatment related integers like the local loop index n and the number of threads and the thread ID and the total number of threads. And there are another few variable functions to get the current thread ID and the current number of threads. And then we set the number of threads explicitly since the code is small and can compile fast. So when we change the thread numbers, we will recompile the code. So we use the OMP parallel environment. In the environment, we need to define all the local variables. Besides what we see from here, we also need to check the macro. We need to include all the local variables mentioned in the macro. We get the thread ID using the OMP command, and we also get the total number of threads from the OMP command, and then the loop index is coded with the thread ID and the total number of threads. So, and the loop index inside the macros also need to be private. And then we close the OMP environment after the loop. So next we will talk about the optimization strategies. We can optimize the SU efficiency, or we can also optimize the wall time of the jobs. So we can treat the KNL device as accelerators, and also we can view it as a high throughput computation device. So for the SU efficiency optimization, the codes reach about 3x allocation usage reduction with pretty out of box. The same benchmark the PI running in production on Stampede1 using 4 nodes. And we can pack it onto one Stampede node. Because on the Stampede1, we have 16 cores per node, and the user use 4 nodes, end up with 64 cores. And on Stampede2, we can use 64 cores on one node. The wall time is just about 30% longer, so it end up to, we just use about 1/3 of the allocation as previously. After applying the OpenMP treatment and fine-tune the code like the vectorization, the reduction is even further. So on the other hand, if we try to push to the limit of time to solution, we can use 4 Stampede2 nodes, put 32 MPI ranks per node, totally use 128 ranks, and reach the best wartime performance. It is about 25% speed up over one node cases. There's more performance data details in the scaling studies in the second part. So the situation of juggling between wartime optimization and SU efficiency optimization and an ineffective OpenMP treatment mainly coming from the fact that the system size of the production benchmark is relatively small. The OpenMP treatment has significant overhead to open and close an OMP environment for if the computational work inside the loop is relatively small. And because this is an iterative process, so we need to open and close the OpenMP environment on every step. If we pick another benchmark list in the PI's scaling study report, which has 4 times higher resolution along one of the angular direction, equivalent to 16 times bigger in the numerical problem size, the OpenMP treatment and the vector alignment combination can contribute to up to a nearly 20% wartime reduction. So on a 2-node cases, as I list below, the OpenMP treatment combined with vector alignment treatment can bring down the view time from 760 to 630 seconds. But the increase in the space dimension of the problem also leads to the increase of number of steps to reach the equilibrium to the solution, which may lead to the runtime exceeds the wartime limits on most of the Stampede2 queue. So also, as suggested in the TACC document, there are 2 ways to keep the core on KNL node busy. The first one is put more than 1 MPI ranks on each core, and the second will be put 1 MPI rank per core plus use the threading treatment for major functions. Ideally, each KNL core can hold up to 4 threads or put 4 MPI ranks. But in most of the case, either 1 or 2 threads reach the best performance. In our case, 1 MPI rank per core plus OpenMP treatment for major functions always wins. If put more than 1 MPI task per core, use closed option for the process binding is better than use the spread. So here are some take-home messages. So porting the code to Stampede2 KNL structure is relatively easy to gain SU efficiency improvements. With enough work for each MPI rank, the OpenMP treatment can contribute further improvements, usually on 2 threads per core case. Usually it's better to use setting treatment than put more than 1 MPI rank on each core. And also profiling report is important to locate the computation intensive sections for the code optimization efforts. So there's more details in the part 2. Thank you.
Thank you very much, Shiquan. Why don't you stop sharing your screen and we'll have Chad put his up. And while we're doing that, are there any questions from folks on the line? I'd see we have a number of KNL experts, including folks who gave our ECSS training over the summer, and we have some Campus Champion Fellows on the line. Anybody want to swap in and ask a question of Shiquan? Yeah, I thought it was really interesting and kind of counterintuitive that you could save on your allocation but take more wall time. I've not seen that come up very often in performance analysis. So that was really interesting and must present some interesting trade-offs for PIs.
Because it uses a lot less number of nodes, but it won't want that much longer. You just want a little bit longer, but you use a lot less nodes.
Right, so the 3-time reduction in CPU or SU usage compared to only, what was it, about a 25% more wall time?
Yeah, 30% around, yes.
Yeah, yeah. Yeah, Lars has a comment, surprised that you had success with more than 1 MPI task per core. This is usually a good recipe for failure.
Yeah, it's, if we use more than 1 MPI rank per core, it's just like 2. If we use 2 MPI rank per core, the performance is better than 1 MPI rank per core at this case, at this code, but it is still not as good as use OpenMP, use 2 OpenMP thread and 1 MPI rank per core. The best case for my benchmark is use 2 OpenMP thread and 1 MPI rank on each core.
Any response, Lars? Would you like to swap in or just?
Yeah, can you hear me? Usually, when users run more than 1 MPI task per core, at some point some error occurs and the fabric goes away and the job fails. But it's good to hear that from time to time, with some codes, there's at least a little bit of success.
Yep, thanks, Lars. Okay, I'd like to introduce Chad, who's going to, oh, here's one more question about whether Intel's fixed vTune on OPF yet. I don't know if
Here's that question too.
No, there are always promises that the next update will fix it. And I think Tommy is going to install some new OPA driver in the next during the next maintenance, but I can't say if that will fix it or not.
Okay, thanks, Lars. So Chad's going to continue the presentation now with going a little bit more in depth in the performance analysis and optimization. So take it away, please, Chad.
All right, thank you. So to provide a little continuity, Shiquan and I were both assigned to this project, and we decided to, well, not really split it up, but kind of do a few things in parallel. And one of the things that we both looked at was the OpenMP treatment. And of course, we ran into the same problems in that we didn't see a lot of improvement, at least initially, with an initial simple parallelizing of some of the loops, we would plateau at around 64 threads per node. So, so I decided to look into what was going on a little bit closer, and the rest of this presentation is kind of the workflow in my process and trying to figure out why we couldn't scale past 64 per node. So I'll go ahead and get started. The outline for this presentation is I'll go into discussing the target architecture a little bit. The PIs previously had deployed this on a Knight's Corner, the KNC architecture, and they had significant problems with throughput, getting memory to the mics, and they were hoping that deploying on a KNL cluster would clear up those bottlenecks. So that's what we were tasked to do, is to see if we could relieve those memory bottlenecks and do what we could in terms of further accelerating the code. So the anatomy of a code optimization process is basically, we look at, okay, well, is it compiled for the target architecture? We'll do a baseline assessment and see where we stand, and identify any optimization potentials. And this includes considering the scale of modifications that either we're allowed to do or that makes sense. So from a bottom-up approach, it could be as simple as adding some compiler pragmas, or if we have complete control of the code and changes to the code, it might involve some algorithmic changes from the top down. So the process in optimizing code is you do an experiment, you do an assessment of the results of that experiment, and iterate. And then I will finish the presentation discussing some avenues for future improvement. Okay, let's see. There we go. Okay, so the target architecture is the Stampede2 cluster, which hosts 4,200 KNL compute nodes. And each compute node has 68 cores with 4 hardware threads each. So that's a total of 272 potential processors per node. So this particular application was run on the KNLs, configured in a cache quadrant mode, in which the fast MCD RAM is managed as a level 3 cache, and the tiles, which there's 2 cores per tile, they're arranged in quadrants in which the addresses are hashed to a directory which is in the same quadrant as the memory. Now the KNLs have, the cores have a clock rate of 1.4 gigahertz, which is roughly half of, say, a Xeon processor like Sandy Bridge. So they're a little slower, but there are a lot more cores per node. There's 16 gigabytes of high-speed MCD RAM, so that translates to a pretty large level 3 cache. Each core has a 32 kilobyte L1 cache. However, the L2 cache of 1 megabyte is shared between 2 cores in a tile. So if we look a little closer at the Knight's Landing node, you can see these 36 tiles. They're connected by a 2D mesh interconnect. And each tile, as I mentioned, has 2 cores, and each core has 2 vector processing units with 4 threads per core. And as I mentioned, the L2 cache is shared between two cores on the tile. The vector processing units are 512-bit, so that translates to 32 single precision or 16 double precision numbers per unit. And they're compatible with a number of vector instruction sets, including back compatible with AVX1, 2, and SSE. Okay. So in order to profile for optimization and get the best performance, we want to take advantage of the most up-to-date vector instruction set. And for the KNL, that's the Mike AVX512. And you can specify this in your compiler flags with the -X Mike-AVX512. This is also available for the Xeons like Skylake, but in that case you would use -X core -AVX512. So for the remainder of the presentation, I'm going to be talking about some of the tools and the procedures that we use specifically for this application, among which are hotspot identification, roofline plots, intranode and internode scaling studies, the application performance snapshot, memory access analysis, vectorization visor, some loop analytics, and the vectorization report. So in order to get a handle on how the code performs on a given architecture, so Shiquan used gprof as a quick analysis of where the bottlenecks might lie, but I prefer to use Intel tools, and their most recent suite of tools, the 28, I forget what they call their suite of tools, but their 2018 tools, including vTune, a really nice, comprehensive, easy to read. So I ran Intel's vTune amplifier, and if you want to do this yourself, I did this deployed onto a compute node. So you take your executable line, or sorry, your command line for your executable, and just insert, in this case, ampl-xe-command line. You can also run this in interactive GUI mode, but to deploy this in batch, just insert ampl-xe-cl. And for this case, I wanted to collect the hotspots. So the result of which you can see in the table below, we have this function stack, and this loop at line 31 in main is the loop that controls the time stepping. So within this loop, most of the time is spent in the Legendre transform function TRA_QST to RTP. So this function took up 19% of the runtime within the time stepping loop. The next two most costly functions, vel transform and mag transform, actually call the TRA_QST to RTP function. So any improvements made there, and for the future, I'll just call this function the bottleneck function to save myself some tongue tripping. So any improvements made in the bottleneck function are going to carry over to the next two most expensive functions as well. Now that we know which function our functions are taking up most of the time, we can get take a closer look using Intel Vector Advisor, which is very similar to vTune. Just insert advix-cl and collect survey. And the result is a more detailed breakdown of the loops within our bottleneck function. And we can see here that the first 3 lines, the first most time-consuming loops, and they occur at line 335, 325, and 316. So the bottom 3 are located in the second most costly function, but we'll just focus on our the identified bottleneck function. So what this loop survey also tells us is the contribution to runtime, vectorization efficiency, which we'll talk about later. It gives us a measure of gigaflops and arithmetic intensity. It can also give us some clues to performance issues. So if we run an additional test to collect trip counts and flops, you can do this by the second line here is insert advex-cl collect trip counts. So with the combination of these two, the survey and the trip counts, we can create a roofline plot, which is a graphical representation of the data in the loop survey. So on this plot, each loop is represented by a dot with a size and color indicate the relative execution time and the call count. The position of the dot, as you can see, well, I hope you can see the text on this plot, but the y-axis is performance in gigaflops, and the x-axis is arithmetic intensity, which is measured in flop per byte. So the position of this dot is measuring, of course, as I mentioned, performance, arithmetic intensity, and both of these axes are log scale. So the roof lines, which are the diagonal and horizontal lines, indicate the level at which possibly no further performance improvements can be made due to bandwidth bounds. So this lower line, I hope you can see my cursor moving there. The lower line is a DRAM bandwidth roof. The solid line I have here is the L2 bandwidth, and then the top dotted line is L1 bandwidth roof. And then we have where we've reached peak computational capability of the architecture. We have here scalar add peak roof, double precision vector add peak, double precision vector fuse multiply add, and single precision vector add peak are there on top of each other. And then the top performance would be achieved with a single precision vector fuse multiply add. So our bottleneck function, which is the one here outlined, involves 2 fuse multiply adds. So potentially we should be, oh, I'm sorry, that's double precision, and it should potentially be able to reach this roof line. So our hotspot and vector analyses tell us how the code behaves on a single MPI rank, but this code, of course, is intended to be distributed amongst many ranks. So in order to get an idea of how this application will behave in practice, we need to do some scaling studies. So the following 3 plots illustrate the behavior of this code on Stampede2. These are weak scaling studies in which we keep the problem size fixed while varying the number of ranks, and we distribute those ranks amongst nodes and threads in a variable manner. So the problem we've chosen is the fixed spherical grid with a discretization of 160 along the 160 grid lines along the radial portion or dimension, 80 grid lines along the theta dimension, and 80 grid lines along the phi dimension. This was presented as an exemplar of the target case that the PIs are ultimately going to be running. So our first plot is was computed on a single node both a KNL core, and I also ran it on Sandy Bridge Xeon for a comparison. So what we see here, this is a speed up plot. So everything's scaled by the performance on a single KNL core. So each plot is the time it takes divided by the time it takes the time it takes at a given number of ranks divided by the time it takes at a single rank. On the KNL, we see that well, on both cases, it scales fairly linearly up until we get to the number of physical cores on the machine. It's interesting to note here that the KNL surpasses or almost meets the performance on Sandy Bridge at 16 ranks. This is somewhat interesting because the Sandy Bridge Xeon cores are almost twice as fast as the KNLs. However, we're vectorized, so the KNL has twice the vector length as the Sandy Bridge. So it's not too surprising to see that we get almost as good a performance at the same number of ranks. But of course, the KNL has 64 cores, so we can improve the scalability considerably past the capability of the Sandy Bridge. As I mentioned, the scaling plateaus beyond the number of cores. So this is pure NPI, and so we have 1 rank per core up to the total number of available cores, and then beyond that, we're adding NPI ranks, more than 1 NPI rank per core. So, of course, we want to see how this scales across nodes as well as within a node. This plot, we arrange each plot line is arranged as a constant number of nodes. So in this case, so a single node is the same. The single node plot is the same as this KNL curve here. So what we see is that we get actual max performance is 0.223 seconds per iteration, and we get that at 128 ranks using 4 nodes and 32 ranks per node. So it's somewhat surprising considering that we got our peak performance on a single node at 64 ranks. So we do slightly better by decreasing the number of total ranks per node. And internode performance, we see that scaling efficiency degrades when we move beyond using 8 nodes. The same plot, if we arrange it in collections of constant processes per node, so rather than a curve being all single node or all 2 nodes, we have the number of processes per node. For example, let's see, this blue triangle or blue diamond, all these plots were done with 32 processes per node. So this would be 1 node using 2 nodes, 4 nodes, etc. And what we can see here is, again, optimal performance was found at the optimal performance was found at 128 total ranks, but we can see that we do pretty well at either 4 or 8 nodes using 32 or 16 processes per node. What this shows us is that we do get optimum performance while underutilizing thread capacity. And so the possible reasons for this is that as we scale up, we're we're suffering from MPI communications overhead across nodes, or possibly we are suffering from core or thread resource contention within a node. So we should figure out which one of those is happening. One way to get a good overview of what's happening with your code is a very simple application called the Application Performance Snapshot. This is also available in the 2018 Parallel Studios from Intel. And you simply just, in your executable line, just drop in APS, and it will produce a report which will change based on really what it determines is your particular issue. So I don't know how well you can see this. I don't think you can see it that well, but I'll summarize it in the next slide. But what it says here is that your application, or let me just clarify. So I ran an application performance snapshot at the knee of our performance curve. So at 32 ranks, at 64 ranks, and 128 ranks. And what it says is that at all three rank levels, it says our application is MPI bound. So, you know, I'm not sure if that's true, but the data that it provides is that the percentage of time in MPI operations is 17%, 20%, 16% at 32, 64, and 128 ranks respectively. So that's how much time it spends in MPI operations. Now, that may in fact be a measure for being MPI bound. However, because it doesn't increase with scaling, it's probably not likely the source of our scaling bottleneck. Is it imbalanced? Well, the report says that imbalance is responsible for between 2 and 4% of the elapsed time for all three rank levels. So, you know, I'm not convinced that MPI is the issue here. Now, if we look at back installs, let me go back and show you the performance snapshots. This line here in the middle, as we increase ranks, it also increases. So there's some correlation between back installs and our scalability issue. So specifically what it says is that at 32 ranks, our back installs is at 38%, and then 48%, and then way up to 71% at 128 ranks. So if it is indeed MPI bound, really this problem is dwarfed by the memory pipeline bottlenecks. So what are back installs? Superscalar processors can be divided into front end, where we fetch and decode instructions, and the back end, where these computations are performed. So during each cycle, the front end generates 2 of these operations, puts them in the pipeline slot, and moves them through the back end. But the actual number of retired pipeline slots that contain useful work is rarely equal to this maximum. And this can be because the back end is not prepared to accept more operations of a certain kind. So this would be a back end bound execution. And there are maybe 2 reasons for this. L2 hit bound is when a significant proportion of the pipeline slots remain empty. So when operations take too long in the back end, they introduce bubbles in the pipeline and can cause fewer pipeline slots containing useful work to be retired per cycle than we can support with the machine. This is an opportunity loss, and it can result in slower execution. Operations like division and memory operations can cause this, as well as directing too many operations to a single execution port. Or it could be L2 misbound, which is a percentage of CPU cycles being spent waiting for L2 load misses to be serviced. Memory requests missing here have to be serviced by local or remote DRAM or empty DRAM, which introduces significant latency. So to get an idea of where our backend stall is happening, we can run a memory access analysis using vTune amplifier. So it's as we did before, introduce ampl xe-cl into our command line. And instead of collecting hotspots, it's time we collect memory access. And the result, if we look here in this table, the second line shows our bottleneck function. And we see that we have 141 million L2 miscounts. And it says that we are 19.3% L2 misbound and 15.9% L2 hitbound. So one possible solution to this is that if we're L2 misbound, that means that we're not predicting, we're having to go out to MCDRAM because we're not predicting memory loads properly. So if we increase prefetch aggressiveness, we might be able to reduce these cache misses by loading the needed memory into L2 in the pipeline a little more effectively. There is a downside to this in that, well, prefetching adds a couple of instructions to the pipeline, and it also you could prefetch branches and things that aren't actually going to get executed, so you'll decrease your pipeline efficiency due to these mispredictions. So to increase the prefetch aggressiveness, you can add this flag -qopt-prefetch equals 3. If you don't have this flag, that means this value is set to the default, which is 2. So we added this flag and we reran the code. And what we find here is that now our miscount drops from 141 million to 3 million, and our hitbound drops from 16% to 0.7%, and our misbound goes from 19% to 0.4%. So the result of this, as we rerun our loop survey and we look at our performance numbers, you can see that our bottleneck function, specifically line 325 of our bottleneck function, improved its performance from 3.8 gigaflops to 5.83 gigaflops. And we can also notice that the other lines within our bottleneck functions have improved their performance numbers as well. And we can visualize this by recomputing our roofline plot. You can see, well, I won't go back to the other plot because it's way up there, but all of our loop markers have moved closer to the L2 bandwidth line. So this reflects across the board improvements in performance. However, because they're still under this L2 bandwidth roof, we don't know if we've actually resolved all of the L2 bandwidth barriers. So the only way that we will know that we have or have not fixed all the L2 bandwidth barriers is to increase the performance of some of these loops. So if we go back and recompute our vector efficiency numbers, if you go into Vector Advisor and pick a loop can request this loop analytics window to come up, and it will tell you a number of things about how well your loop is being vectorized. So, but if we go back, if we look at the survey, all of our bottleneck loops were between 60 and around 70% efficient. We took one loop in particular and look at the loop analytics of line 325 in our bottleneck function. This is 73% efficient. Well, we don't know exactly why it's only 73% efficient. If we look at the actual line of code, just to describe, so this is a loop, but in Fortran it's written as an assignment, but it has it's using vector notation by using this colon in place of an index. So you can think of this line as a scalar loop over the leading index of the vectors involved. So then vectorization, you can think of this, is applied over this loop of the first dimension of the arrays. One way we can get a handle on what's hindering this vectorization efficiency is to look at oh, I'm sorry, I skipped ahead. Let me first define a couple of terms. What are we talking about when we talk about vector efficiency? So first of all, gain is measured as the cost of a scalar loop in cycles divided by the cost of a vector loop in cycles. And then because our expression in line 325 involves float 32 complex values, then our effective vector length is 512 divided by two numbers times 32 equals 8. So the max theoretical vectorization gain possible for this computation is 8 times. So then vector efficiency is the ratio of the actual gain over the ideal gain. So our ideal gain, again, is 8x. So we're looking at, of course, how close we can get to 8x gain. Now, vector efficiency can be hindered by overhead that's sometimes needed to convert these scalar operations to vector operations. So shuffling memory is one thing. And then we can get a look at what's actually going on in the compiler during its automatic vectorization by compiling a vectorization report. We do this by adding to the compiler flags -qopt-report 5. And what this does is when you compile, it will produce a number of files with the extension .opt-rpt. If we look at transform.opt-rpt that was produced after recompiling this code, and we look for line 325, we can see that there are a number of references to memory locations which have unaligned access. And what that means is that the memory there can't be assumed to lie on a boundary which is a multiple of, well, in our case, 64 bits. So then the compiler cannot simply just put these in the registers and run its vectorized operation without doing some memory alignment in order to, well, to line up these vectors or mask them in order to perform its vectorization conversion. So,
Chad?
Yep.
Chad, this is Nancy. It's It's the top of the hour.
Oh.
It's an outstanding talk. I think some people might have to start departing for other commitments, but I'd really like you to complete it if you would like to. I just didn't know how close you were to the end.
Okay, pretty close. I'd say 10 minutes.
Okay, sounds good.
Okay, so what we can do here is, from the vectorization report, see we have unaligned axis. So let's align those variables. Initially, this should be an easy thing to do by adding the flag align array 64 byte that is intended to align the memory automatically. However, this compiler flag only works for dynamically allocated memory. Our code has a significant amount of static and derived data types. So in order to align that memory, you have to go into the code and add the pragma's attributes align 64, for example, and then the name of your variable. So we did this according to what the vectorization report said for line 325. And the result is that now all of our memory accesses are aligned. And our estimated speed up has improved from 5.83 to 7.49. If we look at the loop analytics, we see the actually running the code, we do get a speed up of 7.5%, and now our vectorization efficiency is at 94%. And we also see, let's see if I mention that, our gigaflops have increased to 5.871 for loop 325. If we look at the roofline plot of our optimized code, you can see that now several of these loops are above the L2 bandwidth roofline, so they are no longer, well, they may never have been, but we can at least see now that these loops are not bound by L2 bandwidth. And that being the case, they may be able to be improved by multi-threading via OpenMP. So now, after the vectorization alignment treatment and the prefetching, our newly optimized code is compared with the original code, and we do a scaling study again on Stampede2. Now, what we see is that the trend is the same, but we have improved our peak performance from 0.233 seconds per iteration to 0.191 seconds per iteration for an 18% speed up. Now, the alignment treatment was only applied to resolve the issues with line 325. And we do plan to extend this treatment to the entire vectorization report, so we will likely see considerable additional improvement there. But if we look at the roofline plot again, our peak for potential speed up for our bottleneck loop is this double precision FMA peak, which is way up here at 40 gigaflops. Now we're far from that, and in fact, according to this roofline plot, if we increase performance somehow miraculously up to this degree, we are going to be bound by L2, or I'm sorry, by L1 bandwidth. So if we want to reach optimal speed up here, we will have to increase the arithmetic intensity, and we can do that by well, one way to do it would be by reducing the number of memory accesses per floating point operation. So for future potential improvement, note that the parallelization scheme is well optimized to split up this matrix multiplication of the Legendre transform and evenly distribute it as vector matrix multiplications. This has an arithmetic intensity of 2. However, if we can restructure the algorithm from the top down to bundle these operations into batch matrix operations, we could dramatically improve the arithmetic intensity to n over 2. And I think only by doing this kind of transformation will we be able to reach the peak performance of the KNL. So that's all I had. If you have any questions.
Chad, thank you very much. That was outstanding. A really well-ordered talk. I think sort of a textbook talk for any ECSSer as far as going methodically through the performance analysis path. Folks on the call, questions for Chad?
I don't have a question, just a remark. That was really great insight into how to optimize this code and how to understand what the vectorization does and all these things. I enjoyed it a lot.
Thank you.
Yeah, I agree. Really outstanding. I want Chad and Shiquan to please send slides. We'll post them to the Symposium website, and definitely want to call out this talk in particular to our other ECSSers about a really great way to approach a problem. Got one question for chat here. What do you mean by batch matrix multiply?
So the initial formulation of the Legendre transform involves a matrix multiplication. And what was done in this code to parallelize it was to split this up and sum over a bunch of vector matrix multiplications. Now, if you can back that out and parallelize over the matrix multiplication, you can dramatically increase the arithmetic intensity. So a batch matrix multiplication would be to send well, it is a parallelization of the matrix multiplication. So we're not doing one giant multiplication, but rather several small batches, if that makes sense.
Great. Does that answer the question? You can go ahead and unmute if you'd like, S. Lance.
Okay, sorry. Yeah, I guess I don't have to be so cryptic. Can you hear me?
Yeah.
Yeah.
Okay. So when you say parallelize them, do you mean so they're individually vectorized and you multi-thread the different small matrix multiplications?
Yes.
Okay.
Okay, great. Thanks again, Chad. Thanks, Shiquan. Great ECSS Symposium this month. We're going to skip November because of supercomputing, but we will have a symposium the third Tuesday of the month in December. So thanks very much, everyone.